Okay, so I will start today again with interlacing. Yesterday I showed the first item of interlacing theorem, but I will re-show it today to make sure, because we will need this proof later today. So we already defined interlacing yesterday, and then we introduced the Rayleigh inequality, and so I forgot yesterday. So the UI is the spectral space spanned by U1 to UI. And we can find then W in UI transpose of a perp, which is the orthogonal complement under the norm, this usual inner product. Yes? Okay, now we introduce the interlacing theorem. So you don't need exactly symmetric matrix. You can also allow Hermitian matrices, but I prefer only to look at the real matrices. So for A anti-N matrix, we let it be the N eigenvalues theta 1A up to theta N of A with the corresponding basis of eigen vectors, such that AUI is theta I UI. Now we look at the matrix such that R transpose R is I times the identity matrix of order M. Then we look at the matrix, the symmetric basis B is R transpose AR with M eigenvalues, of course, and they are, M is of course less than or equal to N, because otherwise R transpose R cannot be IM. Yes, because it's M by M matrix. So if that's rank M, then it must be, then N has to be at least M. So then the following things hold. The first thing is that the eigenvalues of B interlace those of A. And if theta I of B is equal to theta I of A, then we can find a special eigenvector. That is what this says. There exists an eigenvector of B, such that Ry is also an eigenvector for A. And this says, yeah, this is, we need 3 for the part of 4. What is the important part is 4. 3 is needed for the 4. We want to show if the interlacing is tight, then AR is RB. And this will be later important to show when this is sometimes a sufficient condition when partition must be equitable. So we define Uj as the vector space spanned by U1 to Ui, and Vj is the vector space by V1 to Vj. So then you see that you have this one. And clearly the dimension of RTUj minus 1 is a mod j minus 1, because if you multiply the factors, it's still they may not be any more linear independent, but that, so the dimension only can decrease, not increase. So that means there must be a non-zero factor in Vi where you and the orthogonal complement of RTUj minus or I minus 1. So this V satisfies the following. You can see that UJTR, so V is V transpose RTUJ is clearly 0, and we can rewrite it as UJ transpose RV for all j from 1 to I minus 1. RV is, of course, in uj, ui minus 1 perp. And RV is not 0 because RTR is times V is V, and V was not 0. And then it follows that we have this inequality. And then you go to minus A and minus B, and then you get the other inequality. That is what we did yesterday. So this shows 1. So now I will use 2. Now I will show 2. So now we assume that we have inequality in inequality 2. So this inequality. That means that all the inequalities are qualities, yes. So then we get a lot of things. Then because you have two inequalities become equality, that means that ARV is theta IA of RV, and BV is AIV, where 0 V is a non-zero factor inside this space, VI intersection with RT UI minus 1 perp. And this is how you show 2. 3 is technical, so but you use essentially 2 by induction. So for I is 1, then you take W1 is Y, where's W1? And probably, okay. Probably I mean here VI, but V1. So we take the eigenvector for, so this is probably V1. Yes, because there must be the one from B. You have only one choice for the eigenvector because that space is only one dimensional. So it must be V1. I'm sorry. So now probably W's are my. So we take W1 is Y in inequality 2. Yes, that's exactly what we did. No, that's correct. W1 is correct. So now we take W1 to Wi minus 1 is Vi minus 1, that span, that linear span of those. Because we want to rename them, because we don't want them to be V1 to Vi minus 1, because we may need slightly different eigenvectors to let it work. The original eigenvectors may not work exactly. That is what is the point here. And we take Uj is RWJ. So we get different eigenvectors, W's and different eigenvectors for A as well. So then we get an Wi in this space Vi and perp of RT Ui minus 1. Just that you have these two inequalities of equalities. And then you show that they are always orthogonal to each other. Here's probably an equality. I forgot here an equality, which shows that they are pairwise orthogonal. This shows 3. Now we do 4, and that is we really use 3 2 times. The whole point is you use 3 in 2 different ways. Namely, you use 3 for A and B, and also for minus A minus B. So let's see what we do. So we have these vectors for where. So we take W1 to Wi such that they satisfy numbers, the item 3. And we do the same thing. So we have this, yes, but this means that this holds. Oh, here is some, oh yeah, yes. This means that we have this. If we go to minus A and minus B, then we get that they are also the same. Yes, and the first J or M minus J eigenvalues of minus B are the same as the first M minus J eigenvalues of A minus A. So we can use the same. So we get this situation. And then we use a 3 again now for minus A minus B. And then we get everything the same. And then you easily can show that AR and RB behave the same on this space of eigenvectors, on this basis of eigenvectors. So then they must be the same matrix. If they behave the same on this set of bases, then they must be the same. Yes. And this is the end of the proof for the theorem. So this shows everything. So this is where the proof we have shown the interlacing theorem. So now I will give 3 examples how to use interlacing and Perron-Frobenius and a lot of you will see later what we will give you some examples now. But here's a very important application is that the eigenvalues of induced subgraph of T interlace the eigenvalues of T. So whatever you take as an induced subgraph, they must always, those eigenvalues must always be interlacing the eigenvalues of T. And if that induced subgraph is not equal to T, then we know also by the Perron-Frobenius theorem that the last eigenvalue of T is larger than the last eigenvalue of this subgraph. So the only way you can get so it's almost never possible that the eigenvalues of an induced subgraph tightly interlace the eigenvalues of T. That is almost never possible. You can think on this problem yourself. So what you do is, so let's assume that our subgraph has the first m vertices of T, and then we can take R is IM, the identity matrix of order M, 0. Then you see that R transpose R is the identity of order M, and R is the identity matrix of the induced subgraph we want. So then we can use the interlacing theorem to show that they interlace. Yes? So now I will give you some examples. The first example is the question, can the complete graph K10 be partitioned into 3 picture graphs? In other words, can we partition the S sets in 3 S sets so that each S set gives you a picture graph? So you can easily see that you can always do with 2. But what is the third graph? That is what we want to show. That the third graph can never be a Peters graph. And the proof is quite interesting. So we have to figure out what is the graph Q. Yes? So we know that J minus I, that is the induced subgraph of the adjacency matrix of K10, is the adjacency matrix of P1, adjacency matrix of P2, plus the adjacency matrix of Q. So if it's not so difficult to see that, with that lemma I gave some days ago, 2 days ago, then you can see that the distinct eigenvalues of Peters graph are 3, 1, and -2. And then if you know that are the eigenvalues, then you can easily calculate the multiplicities, because you have the sum of the eigenvalues will be 0, and the sum of the multiplicity must be 10. And that gives you 2 equations, and that gives you everything. So now we look at we will look at the eigenspace for the eigenvalue 1. Then clearly the dimension of W is 5, because the multiplicity of 1 is 5. Yes. And secondly, because the eigenvector for 3 is an O1 factor. So W is a subset of I perp, of J perp. So now we do this eigenvalue W1 and W2 for P1 and P2 for eigenvalue 1. Both are orthogonal to the O1 factor, and both are 5-dimensional. But the number of vertices is 10. So that means that W1 and W2 are a subspace of a 9-dimensional space. Yes? So there must be a W that is n in W1 and in W2, and that is not 0. And then you can calculate what is the eigenvalue for W for Q. Yes? So you see that AQ is minus 3W. So that means that Q must have an eigenvalue minus 3. But the Petri graph does not have an eigenvalue minus 3. Yes? So it cannot be the Petri graph. So you cannot do this in this partition in 3 Petri graphs. So that is the first example. Now we have to start with some definitions for the second example, because we want to show that something is not Hamiltonian. So, but we need to, for the proof, the line graph of a graph. So what we do is we take as our vertices the edges, and 2 edges are adjacent if they intersect in one endpoint, exactly one endpoint. So that is this. So the incidence matrix of D is a V times E matrix Dij ij, where Dij is 1 if Vi is an end of the edge Ej and otherwise 0. So it's only if it's in the edge, then it's 1, and otherwise it is not in, it's 0. So I did not define this before, but I think everybody knows this anyway. So a closed walk is where x0 is xt, but what is a Hamiltonian walk is a closed walk which has exactly length n, and every vertex of the graph occurs at least once. That means that x0 is xt, but the other ones are all different. And the graph is called Hamiltonian if it has a Hamiltonian walk. And this has had a lot of attention, because to be the property to decide whether it is Hamiltonian or not is an NP complete problem. You may not know what that exactly means, but this is a very important problem. And a lot of people try to find sufficient and necessary conditions for a graph to be Hamiltonian. So now we will use the following result using interlacing. The Petri graph is not Hamiltonian. How can you use interlacing to show that the Petri graph is not Hamiltonian? Yes. So we look at the vertex X incidence matrix of the Petri graph PET. Then you can see that n transpose n is the Artesian matrix of the line graph of Peterson plus 2i, and n times n transpose is Artesian matrix of Peterson plus 3 times the identity, because the Peterson graph is has valency 3. So this has spectrum. The Peterson graph has spectrum 3, 1, 2, 1, 5, and -2, 4. So you add 3, and then you get 6, 4, and 1. So it is in fact that the n transpose n and n transpose have the same spectrum except for the eigenvalue of 0. There's only difference in the spectrum. One may not even have 0 as an eigenvalue, but you can calculate, once you have the other eigenvalue, you can calculate what is the multiplicity of 0. Yes? Because usually n transpose n is not the same order as n transpose. So we get that n transpose n is 6, 4, 1, and 0, 5. And that means that the spectrum of the line graph of Peterson graph is 4, 1, 2, 5, -1, 4, and -2, 5. So far, so good, I hope. This was not so difficult, yes? So assume now that we have a Hamiltonian cycle. Then this Hamiltonian cycle in the line graph of the Peterson graph is an induced subgraph, induced cycle of length n. So now we can use the interlacing theorem, see whether the eigenvalues of C10 interlace the eigenvalues of the line graph of Peterson. Yes? So you can calculate, it's not so difficult to calculate, but this is the spectrum of C10. I will not show this. If you don't believe me, you check yourself that this is the spectrum. But then what is the 7th last eigenvalue of line graph of Peterson is -1. And that's smaller than 1 minus square root of 5 over 2, because square root of 5 is 2.25 or so. So that's minus 1.2, yes, and then you do divide by 2 is something like minus 0.6, yes. So that means that the eigenvalues of the line graph of Peterson graph don't, the eigenvalues of the 10 cycle don't interlace the eigenvalues of the line graph of Peterson. So therefore, the C10 cannot be an induced subgraph of the line graph of the Peterson graph. So that means that the Peterson graph is not Hamiltonian. That was very good, yes. Okay, now we will talk about sensitivity conjecture. This was solved in 2020 by Dr. Wang, and his paper got published in Annals of Mathematics. But I will show the proof today, so in the next 10 minutes or so. So you will see how trivial the proof is. That makes the proof so much better, yes? So we start with the K-cube, yes? This has a graph with vertex at 0, 1 to the power k. So there's factors of length k with entry 0, 1. And 2 of those factors are adjacent if they differ in exactly 1 position. Yeah, here is an example of 3 cube. I think everybody of you have seen this example, probably many times in your life. Okay, that is the 3 cube. So we need also signed line graphs. So you start to, this is an important part of the proof, that you have to look at sign graphs. So So we what is in sine graph is you sign the edges with a +1 or -1 or plus or minus, depends what you like better. Yes. On this moment I say plus and minus, but in the adjacent matrix I will write +1 and -1. So the adjacent matrix is the sign of the edge, and I will add a 1 to make sure that we understand each other. Yes. So now we introduce a proof for the sensitivity conjecture, and this is due to Dr. Wang, and his paper is published in Annals of Mathematics. So this is the theorem he showed. So let gamma be the K cube. So you take W be a set of the vertex set, a set of vertices, with 2k minus 1 plus 1, one more than the half. Yes. Then the spectral radius of the induced shock graph on W is at least squared of k. This was open for a long time, and several people wrote a paper on this, but the proof is, so you will see that the proof using spectrograph theory is very easy. So first step of the proof is, first we will show there is a signing sigma x, sigma k of the k cube, so that if I give the sign to the k cube, then that sign graph has spectrum square root of k to the power k minus 1 and minus squared of k to the power k minus 1, because the adjacent matrix has always a zero diagonal, so the sum of the eigenvalues will be always 0. So we will proceed by induction on k. Yeah. So for k2 we can take k2. Yes. We don't need even signs. That has always a spectrum 1 and minus 1. Yes. So now we assume that we have a signing of the k minus 1 cube with spectrum, the right spectrum, this spectrum we want. So let this be the AK minus 1 be that adjacent matrix. And now we define AK by doing this AK minus 1. We put that on the diagonal. And the other two things we put just identity matrix to the power k minus 1. Yes, AK minus 1, identity matrix, another identity matrix, and then minus AK minus 1. So this is not so difficult, yes? Then you can easily see that AK is adjacent matrix of the k cube for some signing sigma k. But if you now multiply AK by itself, then you see, what do you get? You get the following matrix: AK minus 1 squared plus identity matrix 0, 0, 8 squared k minus 1 plus identity matrix. But then we know the spectrum of this matrix. Yes, because we know we have all the eigenvectors of AK minus 1 have either square root of k minus 1 as their eigenvalue or minus square root of k minus 1 as the eigenvalue. So now if we do VV for that eigenvalue of eigenvector, then we get this KV. So VV is an eigenvector with eigenvalue k. This means that A squared k has spectrum k and that 2 to the power k times. But that means that AK has spectrum square root of k to the power k minus 1 and minus 2 square root of 2 to the power k minus 1. The reason is the sum of the eigenvalues must be 0. So we get this signed K cube. So if we have 8 in induced subgraph, then we can also do then induced time subgraph is when we restrict the sigma to the edges of 8. Yes. So if we restrict the signing of 8 to the 8, then that we call induced time subgraph of the sigma. So now we look at theta 1h and theta 1h sigma h of the losses eigenvalue of h respectively of h sigma restrict to h. Now we need something closely related to the pair-of-base theorem. So it's not exactly pair-of-Frobenius, but so we look at the matrix for any matrix B. We look at the absolute value of the matrix. This means that all the entries are the entries of B in absolute value. So now we want the theta to be an eigenvalue of B, say with unit vector 3, eigenvector 3, and let theta 1 be the last eigenvalue of the absolute value of B. So then what we get is that sigma is sigma phi transpose phi. Yes, because phi is a unit eigenvector. But sigma is an eigenvalue of B with eigenvector B, so we can write theta v as BV, yes? And then we can take the absolute values of all the different entries, yes? So then this, as phi transpose phi is unit vector, phi is a unit vector, we see that this is at most sigma 1. Because we can use the Rayleigh inequality because phi transpose phi is still inner product 1. Yes. So by the pair-of-Frobenius theorem, we get that sigma 1 is at least the absolute value of theta. So now you observe that A8 is exactly the absolute value of A8 sigma restrict to H. So we obtain the last eigenvalue of H is at least sigma of theta in absolute value for any theta of H, eigenvalue theta of H, yes? So this shows that the last eigenvalue. So now we take gamma, the K cube with the sign sigma, so that it is this signing. So let H be the subgraph induced by W, and consider the sign induced sign subgraph H sigma restrict to H. By interlacing, we have that square root of K is theta 1 of gamma sigma. So that is last eigenvalue. But because by interlacing, we have at least 2K minus 1 plus 1 vertices. So we can only remove 2K to the power K minus 1 minus 1 of the square root of K. So we are always left over with at least 1 square root of K. So this shows that the last eigenvalue of H is at least square root of H. And you can have exactly equality if you take one vertex in one side, one of the two parts, and other vertex the other, the other. Say you have the red and the blue vertices. You take one blue vertex and all the red vertices. Then you get the K or the so then you have the K claw in. Then you have many zeros, but you have also one induced subgraph, which is a K claw. This is an induced subgraph of 8. So you can, this bound is sharp. And this shows the sensitivity conjecture. Okay. Okay, we will come back to partitions. We want to give a necessary or sufficient condition that an equitable partition is equitable, of a partition is equitable. So we look at P be the characteristic polynomial, and now we define P, like in equitable partitions, as the quotient matrix, so that's P transpose P minus 1 P transpose AP. There was a quotient matrix of an equitable partition. Now we define that for any partition as the quotient matrix. We can do this. Yes, you get this number. Yes, that this is so this is this sum. Yes. So this means that we get for Bij the following thing. That is the P transpose AP over the norm of Ci. Yes, that is P transpose P. Yeah, the ith part of P. Now we show the following result. So the claim is the eigenvalues of B interlaser of the A. Yeah, B is not even necessarily symmetric. So how do we even know that B has only real eigenvalues? Yes. So, but we show that B is similar to a symmetric matrix, so therefore it has only real eigenvalues. And if the interlaser is tight, then the partition pi is equitable. So we define the diagonal matrix, the square root of P transpose P. You take, we already defined this when we discussed equitable partitions. We will do this one more time. So then you can define, then you can see that P prime is symmetric. Yes. That you see by the expression D inverse P transpose A P D inverse. Yes? Yeah, that's correct. And it's similar to B, yes, because B prime is D inverse. Yes, and D is clearly invertible. Now we define R is P times D inverse. Then it's easy to see that R transpose R is identity. You just do the two equations. This means that the eigenvalues of B, what you really show is the eigenvalues of B prime interlace those of A, but the eigenvalues of B prime and B are the same, so therefore the eigenvalues of B interlace those of A. So there's no misprint here, that's what I mean to say. And now assume that the interlacing is tight. Then APD inverse is AR, is R B transpose of B prime. That is by interlacing tight, and then you write B prime as where is it? That is R D B D inverse, and you can write it also R transpose AR, and that is equal to P times B D inverse. Yes. So that means AP is PB. Yes, because D inverse D is invertible. So that means that P is A invariant. And that we have shown before is the P is A invariant, then the partition is equitable. This means that the partition pi is equitable. So we give the Hofmann bound as an application. So we also call something the ratio bound or Hofmann bound. So in early 2022, Hofmann passed away, and Professor Hamers wrote a paper, a short paper on the history of this Hofmann bound. So this is published in Linear Algebra and Applications. So then you can see what is the history of this Hofmann bound. So, but okay, let's not discuss that more. Let's K be greater than 0, be a regular graph, having a small eigenvalue theta min. Let C be an independent set of vertices and C the order of C. Then the claim is you have C is a most n over K minus over theta minus 1 plus 1. And if equality holds, then every vertex outside C has exactly the right number of theta, namely minus theta minus. Okay, we have to prove this, yes? So let pi be C and the rest. Then the quotient matrix of pi satisfies 0, K minus A for some A. So what are the eigenvalues of this matrix? Yeah, certainly K, yeah, because the row sum is K. So eigenvalue K you have, and then you can easily find the other eigenvalue because then you look at the trace. The trace is equal to A. So the two eigenvalues must add up to A. So then you get the second eigenvalue. So then by interlacing, we know that A minus K must be at least theta minus. Because the eigenvalues of B interlace those of A. And then you can calculate this because K times C must be the same as N minus C times K minus A, yes? And that is because K minus A is at most theta minus theta min. Yeah, we had A minus K, but if you K minus A is at most minus theta min, yes? So we obtain C is at most this number. Yes? And if the equality holds, then the interlacing tight, and hence we know that the pi has to be equitable. And this implies that every vertex outside has exactly minus theta min neighbors in C. So that is the Hofmann bound. Maybe I have a third one. Okay, here's an example. For the Peter graph, we have that alpha is the last size of a co-clique of independent set. And that is because the pentagram has 10 vertices. That says phase is 3 and the smallest eigenvalue is minus 2. So that is 10 over 3 over 2 plus 1. That is 10 over 2.5 is 4. And okay, this is so this goes about coloring, and so you can easily see that if you have the independence number, then you get the lower bound for the chromatic number. That is called a chi of T is called the chromatic number of graph T. Okay, so we have about 15 minutes left. So I will start my part on distance regular graphs. This is probably slightly more difficult. So, but I think the first two sections should not be too difficult, because I mainly give definitions and examples. So we already have seen all these things, but I need that the gamma I of x is the first distance I from the vertex x. That is the main difference. And I write gamma x as gamma 1 of x, they are neighbors. And ki of x is the cardinality of gamma I of x. And kx is the phase d, and that's k1 of x. And we want to discuss the local graph, that is the graph on the neighbors of x. So this is the definition of distance regular graph. So we take x and y at distance I. Then neighbors of y have either distance I minus 1 to x, or distance I, or distance I plus 1. Now I want that the number of vertices at distance I minus 1 from x, neighbors of y, is ci. The number of neighbors of y is distance I from x, I want ai, and the number of neighbors, the other one is pi. So this shows, these are called the intercept numbers of gamma, this pi, ai, and bi. Don't ask me why this order of the letters. Why is not A, B, C? Why is C, A, B? So, but this is introduced by Biggs, and he thought that the AI would be the most important number, and the CI and BI not so important. But it turns out that CI and BI are the most important, and AI is not so important. But that he could not have known in the 1960s. Yes. So gamma is regular with phase B0. We also write B0 as K, and B0 is always equal to CI plus AI plus BI. So you only have to know the number of BI and the number of CI, then you can easily calculate the AIs. That is what we do now. Yes, we take the intersection rates, the B's and the SDs. And note that C1 is always 1. It's very easy. What you can show is that the B's are decreasing and the C's are increasing, but they don't have to be strictly increasing. For example, the B's can, the B's has to have, B1 is always smaller than B0, but if you look at the say 7th one, then you see that B0 is 2, and B1 and B2 are 1, and C1, C2, and C3 are all 1. So you can have everything. So now I will give you some examples. So I will start with the Hamming graph. We have already seen the K cube. And now we make it a slightly larger class of group. Yes. So we take two indices q at least 2 and n at least 1. We take the alpha at 1 to q. And now we take as a vertex set of h and q are the vectors of length n with entries in q. And two of those vectors are associated if they differ in exactly one position. And then you can easily see the diameter is equal to n. If I take q is 2, then I get the n cube. And it's always this rectangle with ci is equal to I. And this gives an algebraic framework to study code, especially bounds on code. For example, you get the delta linear program bound and the Schrijver bound. And we also can define the Johnson graphs. So what we take is we take a set 1 to n, and then we take all the t subsets of n. And you know that by n choose t, capital N choose t. That is the t subset of n. And then two of those t sets are adjacent if the intersection is maximal. If the intersection is now the t minus 1. And you can easily see that j and t is isomorphic to j and n minus t, because if you take the complement of the set, then it becomes then you see that this gives you an automorphism, no isomorphism between j and t and j and n minus. And the diameter of this graph is the minimum of t and n minus t, so we usually assume n is at least 2. And this distance vector graph with ci is equal I squared. And this gives an algebraic framework to study this time. So this is the Hamming graph and Johnson graph. So you see that there are many distance vector graphs. Now I will introduce distance-transitive graphs. They were introduced by, Biggs introduced distance vector graphs and in 1960s, in late 1960s, as a combinatorial generalization of distance-transitive graphs, which we introduce now. So we know what the, so a bijection of the vertex set is an argomorphism if at least the axis is the same. So a connect graph, you official don't need the connectedness, but I prefer connecting. A connected graph is distance transitive if for any four vertices x, y, u, v, such that distance between x and y is equal to distance between u and v, there exists an automorphism phi of gamma with the image of x is u and the image of y is v. So any two vertices at the same distance can be mapped to each other. So you can easily see that a distance transitive graph is always distance regular and hence regular. Many of the distance regular known are distance transitive, but for example, any quadratic form graph of diameter at least 2 is not distance transitive. Almost all the known infinite families with unbounded diameter of distance transitive graphs come from classical objects. So here are some examples. You've seen the Hamming graph, the Johnson graph. The Grassmann graph is essentially the same as Johnson graph, where you, instead of set, you take vector space of finite field. Then you have the bilinear form graph, the Sesky linear form graph, and dual polar graphs. They are all distance transitive. They are all from classical objects. So from my point of view, those objects can be studied now combinatorially using distance vector graphs. There are only 4 known infinite families with unbounded diameter of vertex transitive graph, but not distance transitive. They are not distance transitive, but they are still vertex transitive, and that are called the Ustimenko graphs, the Hammett graphs, the Dub graphs, and the quadratic form graphs, which are sometimes also called the Egawa graphs. Banai conjectured that they were distance regular, and then Egawa showed that they were distance regular. But there's only one infinite family known with unbounded family, with unbounded diameter, which is not vertex transitive, namely the twisted plasma graphs. And this was discovered by Edwin van Dam and myself. And they have 2 orbits on the full argomorphismic group. And they are very strange graphs. Okay, I will stop here with the primitivity section. Thank you for your attention.